Hello, Stats 300 class, and this is Professor Gonzalez, and I would like to do some problems from the assignment side of our work. Of course, using, why is this pencil not working? There we go. Using, having the green box signifying the assignment side coming from 7.4. Okay, so I would like to do a little talk about this before we start. Wow, this pencil is not working today. There it goes. So I'd like to start with maybe a little mini lecture here. This is not working. There we go. This is a sample. We're looking at a sample and proportion. Really proportion, and that's proportion. There's sample proportion, and there's a proportion from the population. So let's kind of break that down. So first of all, I'd like to say that when you see P in this section, or P in statistics, this is the population proportion. This is the population proportion. For example, if we knew that 45% of Americans wear glasses. If we knew that, then we would say P equals 0.45, or, if you want to think of it as a, proportion could be written as a decimal, or you could say P, the population proportion for people that wear glasses, is 45 out of 100 if you want to write it as a fraction, right? But either way, it's a proportion, and that is it's a proportion that comes from the population. It is the proportion from the population. It's not a sample. Okay, and sometimes that is a hard number to get our hands on, but sometimes they just give it to us in some of these questions. Okay. Suppose we perform a simple random sample of 100 Americans. So in the first sample, we find that 39 out of the 100 sampled wear glasses. So using our notation, we've got a notation that P is our population proportion. In this case, this is a sample. Let me change colors for sample. So this is a sample of 100 Americans, and 39 out of the 100 wear glasses. So we would say P hat is the proportion from the sample or sample proportion, and that would be 39 out of 100 people wear glasses. And of course, that could be written as P hat equals, as a decimal, 0.39. Just to kind of talk about that new notation, P hat is our sample proportion. In other words, if we wanted to know, if we were trying to guess what the population proportion was, like it says that the population proportion is 45%, but what if we didn't know the proportion of people wear sunglasses or wear not sun, wear regular glasses is 45%? Then maybe taking a random, simple random sample of 100 Americans at least gets us in the right direction so we can have a starting point to answer that question. It's not perfect. And of course, every additional sample that you do is going to have a different answer, right? Because you're randomly sampling a different set of 100. And that means that this p hat is a random variable that changes. And that random variable can be put in a distribution. Okay, so the other parts to this is that this sample proportion has a numerator, and how did we get the numerator? The numerator that we use is x, and that was just 39 in my example, and x is just going to be the number who have the characteristic. The characteristic that we're looking for. In this case, what was the characteristic? They're people that wear glasses. And then the denominator is going to be n, which is just the total people, right? It's called our sample size, which is the total, right? So the number of people who have the characteristic of wearing glasses out of the total people, 100n, gives us our sample proportion. Okay. So I kind of want to say, so let's see, there we go. So similar to 7.3, remember in 7.3 there were these X bars, right? So that was the sample means from these samples that we did. Similar to 7.3, on 7.4, we have these p hats, which are sample proportions. And what comes with that, that's also very similar, is the central limit theorem for 7.4 also holds true, right, for 7.4. So let's kind of go over that. So with the central limit theorem, it says if n times, so if the sample size times the population proportion is greater than or equal to 10, and the sample size times 1 minus p, that's just going to be the complement of p, must also be greater than or equal to 10. If those two conditions hold, then we get to use the central limit theorem for proportions, or sampling proportions, which gives us all these great formulas to help us out. You've got all these sample p hats, right? Sample proportions. Well, if you take the mean of the sample proportions, guess what it equals? It equals the population proportion. So you've got that. We also have, if you take all the sample proportions, you could find their standard deviation. And how can we do that? Well, we can actually get that information by just taking, let me fix that. By taking the square root of, and of course this is order of operations situation, right? You've got to do the work inside and then square root at the end. But you take the proportion times 1 minus the proportion. So the proportion times the complement divided by the sample size, and then after you divide that, take the square root. And that'll give you your standard deviation of your p hats, or your sample proportions. And then also very important is to connect this these sample proportions to z-scores. And then that allows us to make our standard normal curve with 0 as the mean, and then use our z-tables, which we've been doing since 7.1. So how do you find the z-score? Well, it's just going to be your sample proportion minus your population proportion divided by the standard deviation of these sample proportions. Okay, so all of this is going to be right here for you that I boxed in this section right here, which is 7.4. Central limit theorem of sample proportions. If this holds and this holds, then our sample proportion distribution is approximately normal, which allows us to then use all of these things we've used before with z-scores and everything, okay? It really opens everything up for us. Let's go ahead and tackle our first problem. Okay, so here it is. Oh, there we go. Our first problem says, okay, first of all, it says the National Coffee Association reported that 61%, so reports that 61% of U.S. adults drink coffee daily. Okay, so it doesn't say anywhere in here about a sample yet, right? The National Coffee Association reported that 61% of U.S. adults drink coffee. So this actually is going to be a p value, a population proportion. And let me, I don't know why I want to do this in a different color, but I'm going to do this in blue. So I'm going to say that p equals 0.61. That's the population. Now then it says a random sample of 250 adults is selected. Okay, so that means now that n equals 250. Okay, so far, what do we have here? Well, in order to really use the central limit theorem here, we really do need to go through, in order to use the central limit theorem, we really kind of need to go through and show that this is true. What do we need to show? We need to show that n times p is greater than or equal to 10. Well, our n value is 250, and our p value is 0.61. And when we multiply that, we get a pretty good size number, 152.5, which is definitely greater than or equal to 10. So that part's satisfied. Then we've got our n times 1 minus p, which is just the complement of p. So we've got sample size 250 times 1 minus 0.61, which is 0.39. And when you multiply that, we get 97.5, which is also greater than or equal to 10. So that is satisfied. So now we get to use all the formulas in our central limit theorem. So how are we going to find this right here? Well, in our central limit theorem, let's just go down there and look real quick. The mean of the p hats, or the mean of the sample proportions, is just equal to the population proportion. Oh, well, we're given that. So we can just work our way back up here. The mean of the sample proportions is equal to the population proportion. Well, that is right here in blue. So our answer is already just in front of us. Just have to know where to look. So there's our first answer. The mean of the sample the mean of the sample proportions is just 0.61. Part B, what we want to get this standard deviation of the sample proportions. And once again, we can look that up over here on our little table, our little note card. And there it is right there. All right, so I can work this. I'm going to do it right here. This is going to be part B. And actually, let's see, I had space. I didn't have to cram it in here, I don't think, because I'm using, let's see, let me just do this. Just to show you, this stuff down here is going to be on the next page. So, all right, well, I'm right here anyways. Let's just do it here. So B is, we're going to take the standard deviation of the sample proportions by our formula. Says it's just the square root of P, population proportion, times its complement divided by N. So what does that look like? That is going to be, our p-value is 0.61 times the complement of 0.61, which is 0.39, all divided by our sample size of 250, and that gets square rooted. And so if you put that in your calculator, then divide by 250, and then hit your square root button, we will get an approximate value, let me say approximate value of approximately 0.0308. Okay, so now let's go ahead and work these other problems. See down here, I kind of made some space. So what are some of the values that we need for this? Well, we need to know that P equals 0.61, the population proportion. We had our sample size is 250. We also figured out from part A that the mean of our sample proportions is just the population proportion also. So that's just 0.61 also. And we also found the standard deviation of our population proportion, the standard deviation of our sample proportion is approximately equal to 0.0308. Okay, that gives us, and then we already established that we're allowed to use the central limit theorem because of these two pieces that were satisfied. Okay. Once again, how do you read that on the note card? Well, it says right here, you get the central limit theorem for proportion or for sample proportions. If this is satisfied and this is satisfied, then p hat distribution is approximately normal. And once it's approximately normal, we can use z-scores and all these other things with it. Okay, so let's go back to our problem. And what is our problem? Okay, here's really, I think, the tricky part of the sample proportions. We're kind of used to seeing things like 65% as being the proportion under the curve or the percent under the curve. Now here's where it does get a little bit confusing because that's not what we're talking about here. We're talking about, let me see if I can move this down. We're talking about, well, first I better read the problem. Find the probability, and the probability is going to be the thing that's the area under the curve. Find the probability that more than 65% of what? Of these sampled adults. So this 65% is actually a p hat, right? It's a sampled proportion, and sample proportion, you could think of it as 65 out of 100 or just 0.65. But our p, so we got a p hat here. On this problem, our p hat is 0.65. So remember, p hat is the proportion from a sample, and basically what they're saying here is we've got a bunch of sample proportions, and 0.65, that's just one of them. And by the way, we also know what the mean of all the sample proportions are. It is this guy right here, right? That is the mean of all the sample proportions right there, which is 0.61. And so 0.65 is to the right of that. And I'm going to do that in red, I think. So that is a p hat. And there are a bunch of p hats here, right? But that's the particular one that we're looking at. And we're saying find the probability that more than 65% of the sampled adults, these are all p hat sampled adults, drink coffee daily. So we're looking for the answer to be more than this. So we're looking to the right. And if I could figure out what this is, oh my gosh, I just erased everything. There we go. If I could figure out what this is, I get the answer to my question. Now the problem is I don't have any z tables that have 0.65 proportions in them. These are all p hats. Remember, these all everything labeled on this sort of number line, I guess, are proportions from a sample. Okay, I don't have any z table or any kind of table for that. So what I have to do is I'm going to have to convert this into, well, I just thought of something. Well, I thought maybe I could copy it, but now I'm just going to redraw it. I'm going to need to convert this into, right, the same exact drawing, but instead of having p hats, right, it's going to have z-scores. So I'm looking for this right here. Essentially what I need to do is I need to take this guy right here. I'm going to get rid of some of this stuff because it's kind of in my way. I need to take this sample proportion and convert it into a z-score using my z formula. Once again, we can just kind of mouse down here and find the formula for when you're talking about sample proportions and trying to convert to z-scores. There it is right there. Okay, so we can use that formula. And that is going to be p hat. Now, what is our p hat? Well, our p hat is this 0.065 that we're talking about right here, right? Our sample proportion. And then what we want to do is we want to subtract out our population proportion, which was 0.61. And then we want to divide it by our standard deviation of our p hats, which is 0.0308. And we divide that and we round and we get approximately 1.30. And so now this new number here, we'll go, I don't know why I changed colors. This new number is now a z number. And that I can now look on my z table. And remember, when I look on my z table, it's going to give me the area to the left of that z number. And so when I do that, I end up getting 0.9032. Of course, to get this stuff in black, I've got to subtract it out. And we've done that a bunch of times. And when I take 1 minus, when I take 1 minus, of course, this red stuff, 0.9032, this red stuff is actually the area under the curve to the left of that. Whoops, now I messed up. That gives me, way too big now. That gives me this answer, which is 0.0968. Must have selected a thicker. And that is the area. So that's answering the question. Find the probability that more than 65% of the sampled adults. So once again, when we're looking at, I need to make this smaller. I guess there. So when we're looking at the 65%, this is a p hat there, right? It's the sampled adults, so it's sampled proportion. Once again, 65%. 65% can be thought of as 65 out of 100, definitely a proportion, and also could be written as 0.65 or 65 hundredths. All right, let's do the next one. Find the probability that the proportion of sampled adults, so we're still talking about p hats, who drink coffee daily, is between this p hat, right, that sample of 50, that sample proportion of 0.59, and this sample proportion of 0.68. So, this particular drawing is not super essential, but I think it kind of is for mentally thinking about what's going on, because what's going on here is we're basically making a distribution with our p hats, right? And we do know that the mean of the p hats we found out way back at the very beginning of this problem, and that was, or is, 0.61, and we want this to be in between about there. I'll do that one in green. 0.59, and this one, which is about here, something like that, which is 0.68. And once again, these are sample proportions. These are p hats. Okay, and they're asking for us to figure out the between. So that, of course, is this stuff right here. Okay, once again, we don't have a table that'll do this for us. We're going to need to convert these numbers into z-scores. So if we take the sample proportion of 0.59 and subtract out our population proportion, which is also the mean of the sample proportions, 0.61, divided by the standard deviation of the sample proportions, which is 0.0308. And we're going to get approximately negative 0.6, round up to 5. That's a z-score, so be careful. That looks like, it looks like a percentage or proportion, but it is negative. So that is definitely not the area under any curve or anything like that. I think I'm going to go ahead and make this over here so we kind of see where it belongs. And now this is going to be a standard normal. That's 0. This is going to be our corresponding green. Now z-score negative 0.65. Of course, when we look that up, it gives us the area to the left, but we really want the area in between. So let's figure out that proportion or sample proportion converted to a z-score is going to be z equals the p hat, which in this case is 0.68 that we're converting, minus the population proportion, 6.61, divided by the standard deviation of the p hats, which is 0.0308. And we throw that in the calculator, and we get approximately, rounding to 2 decimal places, 2.27. So this is, we're probably way out here at 2.27. And they want us to find the proportion, or find the probability of these sample proportions that are in between. And so we are looking for this shaded, dark shaded region is what we're looking for. So we've done this sort of many times at this point, this procedure. Now look up negative 0.65 as a z-value. And when you look that up, you will get an area to the left, which is the green area, 0.2578. And just like we've done many times by this time, we look up a z-value of 2.27, and that's going to give us all this area over here, which I can say is this area. I look it up, 2.27 as a z-value, and that gives me an area of 0.9884. So of course, I subtract the red from the green, and I get my resulting shaded value, which is 0.7306. And that is the answer to that problem. Okay, find the probability that the proportion of the sampled adults who drink coffee daily is between a sample proportion of 0.59 and a sample proportion of 0.68. And we did it. The probability is 0.7306. Let's do the next one, E. Find the probability that less than 68% of sampled adults, once again, when they say 68% of the sampled adults drink coffee daily, they're talking about a p-hat again of 0.56. So now you're starting to kind of see what's going on here, trying to get a visual of what's happening here. Once again, I am going to take all of these samples, right? There's going to be a bunch of these samples that sample adult coffee drinkers. And so you get all these sample proportions, and then we make a distribution out of it. And once again, we already know the mean, because that was found in part A, which was 0.61, is the mean of all those sample proportions. And they want to know, okay, so we've got a sample proportion of 0.56, that's to the left of that mean. And they want to know the probability that less than this are coffee drinkers. So now we need to find the area to the left of this sample proportion of 0.56. Right? Well, the nice thing is our z-score is going to give us the area to the left, but this is not a z-score yet. So we need to convert this into a z-score. This has got to be converted into a z-score. We will do it right here. So we've got a z-score of our sample proportion of 0.056 minus population proportion of 0.61 divided by our standard deviation of those sample proportions, 0.0308, and put it in the calculator, round it, and we get a negative 1.62. That is our z-score. Now this is something I can deal with. This is now a standard normal, 0. This is a z-score of negative 6.2, and I want the area to the left because it said less than that sample proportion. And so when I look that up, I go to my z table, I look up a negative 1.62, and I get 0.0526. And that's the answer. Now this last one is doing the same thing again, but then they want to know, is this unusual? And for something to be unusual, it must be less than what? 0.05 or 5%, right? If the probability is less than 5%, we call it unusual. Now, they're talking about, would it be unusual if less than 54% of the sample drinkers, would it be unusual if it's less than 54%? Okay, so, well, 56% was already at 0.0, it's just a little bigger than 5. So my guess is if we drop to 54%, that it's going to be less than 5%, which means it would be unusual. But I can't just guess. I got to actually do it, right? So we're going to do the problem again. It's not the same problem, but it's the same procedure. And so this very last problem, well, let's do it again here. So what we have is our distribution of our sample proportions. We do know that the mean of the sample proportions, just like every other time, and this problem was 0.61, and this particular one we are down here at 0.54. And our question is that area less than 5%? And if it is, then it's unusual. If that area is bigger than 5%, then it is not unusual. Okay, well, let's check it out. We have to convert this p hat into a z value. We can do that in an easy way using the formula, 0.54 minus 0.61 divided by 0.0308, and we get our z value as approximately a negative 2.27. Now when I take a look at this picture as it is a standard normal now, meaning 0 is the mean, and we've got this negative 2.27, and we're trying to see, is that unusual? We go to our z table and look up a negative 2.27, and we get an area or a probability of 0.0116. Now we move the decimal to the right 2 places, and that's just a little more than 1%. So we could pretty confidently, very confidently say that, let's use another colored pen, it would be unusual if less than 54% of the sampled adults drink coffee daily, since the probability is 0.0116. You could write that as a decimal, or if you just wanted to write that as 1.16%, that would have been okay too. And that is it. So I really think once you grasp 7.3 and this whole idea of the central limit theorem, and the central limit theorem, it really builds on itself with 7.4. Really, I think the big jump, and it probably is really useful, I think, to draw these pictures of the normal distribution of these sample proportions, realizing that these sample proportions of 0.65 in this case are actually the label. It's going to be, these sample proportions are the labels down here, not the areas. I think that can be very confusing, but I think once you get that, and that you realize you just have these sample proportions like 0.65, and you put it in your formula, turn it into a z-score, now you're back to 7.1 and 7.2, and it's all same stuff again. So it's just a matter of being able to interpret that. And like I said, I think the key really is, looking at this chart. The book doesn't exactly put them in boxes, but I really wanted to put them in a box and then have this little if statement showing that, once this is satisfied, you get all the benefits of the central limit theorem. Okay, well, I hope that was helpful on 7.4, and I'll continue to crack out more of these homework problems on 8.1 and 8.2, and I hope you are having a safe and great day. Take care.